Dr. Anish Bekal give a guest lecture on gas spectroscopy today. Just start with a brief introduction and then we'll go into the talk. Dr. Anish Bekal received his bachelor's degree from Manipal Institute of Technology. That was in 2004, beyond which he worked for the Indian Space Research Organization for about 3.5 years on phased array antennas and communication systems. And after that, he joined IIT Madras for his master's and then eventually his PhD. And that was actually on mode lock fiber lasers. He graduated in 2014. Since 2014 or 2014 to 17, he was working with the GE Global Research Center, and a lot of his work was focused on trace gas measurements, some of which he will possibly talk about today. And presently, he is working as a technical specialist in developing technologies for industrial applications with a unique mix. So he's got his background on RF, microwave components as well as optical components. So he tries to, get things together and whatever can solve a particular problem for Forbes Marshall. He has 12 journal articles and conference papers and 7 patents, well, patent applications at this point, but eventually be patents, I suppose, to his credit. So without further ado, I invite Dr. Anish Bekal to give his talk.
Thank you, Dr. Balaji. Thank you for introducing me. And I think out of that 7, I think 3 have already been converted into patents right now. So that's just to add to what you said. Good morning, everybody. It's nice to have this kind of talk where I can give you an industry perspective of things that are happening, things that have especially in absorption spectroscopy domain, which I think not many people in the country are aware of in terms of its application in real world situations. So this would be a good gateway for many of you to look at how these technologies are actually used in the industry, in industrial applications. Okay, so let me just jump into my slides right away. Okay. Okay, so let me share my screen. I suppose everybody is able to see my screen.
Yes, Anish, we can see
it's coming up. Yeah.
Okay, so the main idea of today's discussion would be optical spectroscopy in industrial applications. You might have seen spectroscopy being used in several areas. Actually, it's used quite a lot in physics space to determine molecular structures or atomic structures or even atomic clocks and things like that. So we will kind of look at how it is used in industrial applications, especially in emission monitoring. So what are we discussing today? The most important thing that we're discussing is the spectroscopy is a science where fundamental properties of materials are revealed through their interaction with light. So that is the basic idea behind spectroscopy. It is to basically find out what material it is or what gas it is by its interaction with looking at their interaction with light. It's actually used in wide array of applications. You might have heard sentences, especially from astronomy community, where they say this particular planet has this particular atmosphere, it is methane intensive, or what do you call, Mars has no something does not have any atmosphere, or some has high carbon dioxide atmosphere. How do they know all these things? They know all these things because of absorption spectroscopy. They basically look at the background sun or background star light passing through the atmosphere of a planet, and then looking at what lines are basically missing in those in the absorption spectra, and that kind of gives them an idea of what is the atmosphere of that particular planet. That going to the what do you call, mega level, to what has become a very important life-saving tool nowadays, under the situation of the pandemic spreading, is the pulse oximetry device. That also is basically an absorption spectroscopy device, which looks at the oxygen absorption at IR and the red color region, the visible region. Looking at that, you can determine the oxygen saturation level. So there's a wide spectra of applications where spectroscopy is used. So today we shall discuss about the industrial applications of spectroscopy, more focused towards many things that you need to do before you actually do spectroscopy, and then we'll talk a progression of optical technologies that has been part of the spectroscopy domain. Okay. So this is the roadmap. Just to give you a first, we'll talk about the spectrum, molecular vibrations, and the typical power plant setup, the SOX-NOx measurement, what are the typical specification that we ask for, then UV-based spectroscopy. Then we'll also talk about gas filter correlation, then a selective catalytic reactor, what is that, and why measuring ammonia is important. Then a technology called wavelength modulation spectroscopy, and then the actual measurement system, and then the conclusion. At the end, I'll also show you what is important is to understand, if we do not do few things that we are talking about, what happens. Okay. That is kind of important in the sense that we always show it in all working scenario, and I would like to show that a non-working scenario also, but at the end, so that what do you call, it can be better compiled and better appreciated. Okay. So let's talk about the electromagnetic spectrum. This was one of the images that I got, which I felt was very very representative of what we use this for and why it is important. So the entire electromagnetic spectrum has one application or the other, right? So we start from radio waves, AM radio, which is at a megahertz or so, right up to gamma rays, which is used in atomic nuclei, or the nuclear power measurements, nuclear power applications, electricity generation, and things like that. In that whole range, there is a wide spectrum of applications that exist between this whole range of things. What is very nice about this particular image is that it also shows the absorption spectrum of the atmosphere, which is predominantly water, overlapped with this spectra, and why these things are very important. If you look at this, there is severe absorption up to the radio waves. Then there is a radio window where most of our applications of telephone, FM radio, all those things happen in this region. And if this window was not existing, then it would have been, the whole mobile communication world would have been very different compared to what we are seeing right now. Okay, and then you have microwaves, then you have infrared, and there is another optical window that comes about in this region, and that's one of the possible reasons why our eyes have evolved to basically look at visible light the way we had. Maybe if this window had shifted, then we would be looking at very different absorption spectra, and the world itself would have been very different because of the properties, chemical properties they induce. Okay, so it's so important that there is a window here which does what it does. And then you have the ultraviolet region. So most of our applications, most of our choice of wavelength is heavily dependent on these windows. Okay, so you have wide range, and even when we do gas spectroscopy, we kind of choose to be in one of these windows, or we kind of remove the interference that are required, that are present in this spectrum, so that we can look at one particular region of one particular molecule or one particular chemical. Okay, so why does all this happen? That is happens because of something that Einstein had proposed in the time frame of 1905, that whenever there is an electron, what do you call, in an atomic system, when the light or the radiation gets falls on a particular material, it absorbs that particular radiation and then emits out in the same frequency, same wavelength or same frequency. Right. So when this particular thing happens, there is absorption and then there is emission. What is important for most of our application is absorption is kind of even though it is not a directional phenomenon, but you can basically put a transmitter and receiver and basically find out what is the absorption, the amount of absorption that has happened. Whereas emission actually happens at any of the 360-degree angles, so it is harder to measure. So most easiest way of measuring this phenomenon is absorption. Of course, emission is used in Raman spectroscopy or any and similar technologies of fluorescence or anything of that sorts. However, it is harder to measure. Absorption is easier to measure because you know the direction in which the light is propagated. So absorption comes in, and then there is emission. So when this emission occurs, when this absorption is measured, so this actually does not happen only in an atomic system. It actually happens in any system. Okay, in any system which has multiple body interaction. Okay, so if you have things like, for example, this is an oxygen molecule, and there is a huge, there's a very large atomic number oxygen, and then there are small atomic number hydrogen that are connected to it. So once you have this 3-body system or even a 2-body system, you can have different kind of vibrations that can occur in that. You could have symmetric stretches, you can have asymmetric stretches, you can have bends, you can have rotations, you can have rotation across all 3 axes. And all these components of this is I'm still talking in terms of classical mechanics in one sense of the way, but all these kind of vibrations you can imagine as a spring-based spring and a body vibration, which will tell you which all require certain energy, and whenever there is a radiation falling on it, of that particular energy, they get absorbed and then form either heat or convert into any of these vibrations. So these vibrations are, as you see, they are what do you call, they are dependent on the mass of each of these atom or each of these molecule, and they also depends on this length, which is dependent on the force that is exerted between the 2 atoms in terms of the bond that has formed. And because of this, the features that come about is very unique. Okay, so every molecule can have, of course there are overlaps, but every molecule will have in general a unique set of absorption frequencies, which can be absorption frequencies which what do you call, which can be identified to a particular material. Okay, so that is where the spectroscopy becomes important, because you can say if you have a set of 10 or 15 absorption points wavelengths which has got absorbed, you can uniquely actually say that this is because of this particular material. Okay, so that's a nice thing about having an optical spectroscopy system. So there are several applications that I was talking about, and I was telling, though some of the applications is in moisture measurement. For example, you buy LPG cylinders in your house, and most of them we just buy it and keep it at home. But imagine a large consignment or a pipeline is laid for LPG to flow or natural gas to flow, and there is transactions of billions of dollars that happens between the oil producer to the refinery or anything of that sort. And as you know, as they remove oil from the wells, there will inevitably a lot of water, right? So a refinery or anybody who is buying it does not want to basically pay money for water and buy only based on the enthalpy value or based on the calorific value of that particular fuel. And that would be a moisture. So you need a measurement of moisture, and optical technologies are one of the very important technologies for measuring this moisture content. Second is emission monitoring. So you have emissions from power plants which are to be regulated, and most of our talk will be based on that, so I will not spend a lot of time here on that. Also, you have corrosion detection. You have hydrogen sulfide forming in the hydrogen sulfide, which is in the which exists in small parts in natural gas, can basically corrode the metal that exists of the metal of the pipe and lead to explosions. Several explosions have occurred because of corrosion, and even concentrations as low as 4 parts per billion is sufficient to cause cause corrosion and explosion of the pipeline on long term. It won't happen the day you install it, but it will happen over years. But it can be very catastrophic. So you can measure H2S and form corrosion detection. Transformer condition monitoring. Whenever you put transformers, you might have seen transformers exploding, and there are several studies and also equipment which can detect the gases that are coming, the hydrocarbons that are coming out of the oil that is used to lubricate the transformer, and that can give you an indication of whether the transformer is decaying, and you can measure that. Then explosive detection, RDX, TNT, or any of these chemicals, they all have nitrous bonds, nitrogen oxide or nitrogen bonds in them, and you can detect them, detect the explosion, detect the presence of an explosive by looking at these bonds and do that. Okay, then of course the industrial process monitoring, same, you can measure alcohols, you can measure it's quite a lot used in beer industry, or it is used in even sorting apples, whether they are ripe or whether they are still to be kept in the storage and things like that. So there are several of such applications, and this is one of the exciting applications of in fundamental physics. There are instruments on Curiosity and Curiosity rover from NASA, which looks at the amount of methane that is present in the Martian atmosphere, which again is a spectroscopy based instrument, and uses one of the techniques that I am going to explain, called TDLAS, or tunable diode laser spectroscopy, which this is basically an image of Gale crater methane levels over different points in your different points over the year. It can measure, as you see here, it can measure 1 part per billion kind of concentrations that are there. Okay, so it's kind of this area is very fertile. in terms of applications. And now, since the availability of many of these kind of lasers, it is becoming more and more important. Even now we can talk about optical combs or clocking. They are also what do you call, connected to certain absorption lines and things like that. So it is kind of important. Okay. So before we go ahead into application, it is very important that you understand why these applications are important and where they are. What is the structure? What is the what do you call, background, or what is the place as such where these applications are installed? So let's talk about a power plant. Okay, so everybody gets electricity, and it all comes from different types of power plants. It could nowadays there's a lot of emphasis on solar and wind, and before that we have been using coal-based power plants, and also waste-based power plants and things like that. And these power plants are what do you call, are very high amount of pollution comes out of these power plants. And basically what happens is you have deposits of coal that gets transferred from the mines to the industry, and this coal is basically taken into the plant, and they basically are solid blocks of coal, and they are pulverized, pulverized and made into small, very small bricks, very small particles, and they go in and they are ignited. Okay, so once this ignition happens, the temperature can go as high as 2000 degrees centigrade, and now you have tubes of water that are inside the boiler. Inside goes into this heated chamber or the furnace, and once they are heated, water boils into steam, and the steam goes into a turbine, and then the turbine runs an electric generator, which is for part of the turbine, and then goes into transmission line and into our house and into our homes and industries and things like that. Where our optical senses become important is this area. Okay, so as soon as when you have when the coal basically mixes with air in order to combust, it generates extremely large amounts of pollutants, like carbon dioxide, carbon monoxide. Then if there is sulfur in coal, then there is SO2, yeah, then there is NO2, then there is nitrous oxide, water, of course, is a byproduct, then HCl, hydrogen fluoride, hydrogen sulfide. All these things basically go out of your chimney. And nowadays there is a very strict regulations that are coming in place in the country, which has already been implemented in many of these plants, in order to, so which are basically trying to reduce these emissions. Okay, so these emissions are basically causing all our pollution effects, the global warming and things like that. So these emissions are very important to be controlled. Okay, now we say, I want to measure this. How do you measure this? Okay, there is a multitude of technologies that exist to measure these gases. And typically, as I was telling you, these temperatures can go anywhere above 1600 or 2000 degrees centigrade. But by the time it comes to the stack and comes out, there typically can be two different kind of scenario. Okay, one is called a dry gas, where dry in the sense that all the water content that is there is in the form of a vapor or steam. So we call that dry gas, and that happens if the gas that is coming out is at greater than 80 degrees centigrade. And then you have something called wet gas, where the things have cooled down to less than 80 degrees centigrade, and the challenges that exist are very different in these two kinds of measurements, and you have to be very specific about what kind of auxiliary systems you should have in order to measure these. Okay, then of course, when you try to measure it, for example, if you can think that I could sample some amount of gas, and that is done quite often, called isokinetic sampling. And you have to be very, very careful when you are doing that. For example, when you have water and you have hydrogen sulfide or SO2 also as part of the mixture, and you cool it down in the presence of water, you will end up with sulfuric acid. Okay, so when you try to measure the gas, you may not get a large concentration of SO2 at all, because all those things would have got converted into sulfuric acid. Similar is the case when you have NO, which becomes nitrous oxide, or which changes over to nitrous oxide, or you can have nitric acid forming. So you have to be very, very careful such that these chemical reactions do not occur. And once these chemical reactions occur, you will have troubles measuring these concentrations directly. Okay, it is not only just spectroscopy that is important, it is also how you extract this gas also important. And there are two technologies that are very important, rather three. One is called in situ or cross-stack. Both of them I would combine inside in situ. And then there is hot extractive. There is actually anything called cold extractive, which is also very much in vogue. But I will not dwell a lot into that technology as such. But these two are right now very important in measuring these, because they are the preferred choice of measurement. Okay, so I'll explain you what they are. Before that, typically when we say an analyzer, what is the specifications of these? Okay, what are we looking for? We are trying to measure SOx, NOx. Then we measure CO, CO2, water, oxygen. All of these are being measured. Typically, the ranges of these sensors are 0 to 100 ppm, or 0 to 250, or 0 to 500, or 0 to 1000 ppm. That is the range that we are talking about. Just to give you this one, so we are talking about ppm. So there is in a million molecules of the base gas of, for example, nitrogen or air or anything of that, you are trying to detect 100 parts of a particular chemical in this what do you call in this in this million parts of other gas, right? So it's a very, very trace amount that you are trying to detect. And there are technologies which go beyond this, where we are talking about ppb, or 1 part per billion kind of traces, right? So so when we are talking about this, so you have 0 to 100. So agencies typically say that the sensitivity that you want should be 2% of the full scale. That is very important, because when you have this range, have 0 to 100, and our minimum resolution that we offer is only 10 ppm. That is not a very good sensor, because you get only 10 points between 0 to 100. So what government agencies basically ask for is something which is of 2% of the full scale. And so if you look at that, then I should be able to measure 0 to 2 ppm at 2 ppm sensitivity for this, 5 ppm for this, and then equivalent. So 1000 ppm, you're talking about 20 ppm kind of sensitivities, or here you're talking about 10 ppm sensitivity. So when you say I have a range of this sensor, so you should make sure that sensitivity is less than 2% of full scale. And when they say sensitivity, this is beyond all interference, all fluctuations, everything. So you put interference, you put fluctuations, changes because of temperature or anything of that sort, they all have to come beyond 2% of the full scale. Detection time, 200 seconds, they typically allow. But for some applications, we want as low as 1 second. And then they also want a requirement that your sensors should be available 90% of the time in the day. So that is also very important for us, because every day you would require a calibration of the instrument, and you would spend rest of the 10% of the day possibly in trying to calibrate. And nowadays you also you should be able to remotely zero. That means CPCB typically says that if I send a command from CPCB Delhi, for example, I should be able to do a zeroing on the instrument remotely, or a span check of the instrument, or and all the data has to go to the central pollution control board directly without any interference in the middle. So when you say a sensor has to be built, it is now a summation of multiple technologies or multiple areas, starting from IoT to spectroscopy, to electronics, to mechanical systems. So all these technologies have to come together to form one of these systems. So it is very important to understand the interconnections between them, the constraints offered by all of them, and then kind of make the system work. Okay, so let me just go across all these three types of analyzers that exist and tell you which is good. So this is, for example, an example of a cross duct analyzer. So what happens is the gas basically flows like this, and then the light basically moves from the transmitter to receiver, and then in this process it is actually passing through the gas, and you are measuring the properties of the gas. It is relatively easy to install, even though the temperature of the gas can be anything, and it's now separated by a window, so you don't need much high temperature optical surfaces. And since you are measuring the sample at the place where the sample is being propagated, it's a very, very good representative of the sample that comes. Okay, and it also has a very fast response, because the path lengths in this region can be anywhere between 6 meters to about 2 meters to 10 meters, 6 meters. So this offers you an advantage of very large path length, where you can measure this one. So I suppose people will remember something called Beard-Lambert's law, which basically says the absorption is proportional to the exponent of the concentration and the path length that you over which the light propagates. So now you're talking about increase in path length, which will give you good absorption capability. But however, it has a lot of disadvantages. So if you have a high dust load, and some of these applications are such that you cannot even see through. Okay, so in such conditions, it becomes very hard to measure any of these concentrations. And these stacks are not really static systems. As soon as the temperature starts increasing, this whole stack wall, which you think is made out of concrete or steel or titanium in some cases, they actually move, because the power plant is vibrating, power plant is hot, and this whole plant can actually twist or move by certain millimeters, and this causes severe problems in terms of alignment. Okay, when you have these kind of systems, and then you have in some cases a true zero is not possible, because if you want to take a zero here, in this case, you have to wait for the plant to shut down, or even the span calibration. So span calibration, when I mean, is I basically want to put a fixed concentration, for example 100 ppm of the gas in this path, and see what the instrument is measuring. That's one way of telling whether the instrument is working. So all those things are very difficult in these kind of schemes. This is another type of analyzer where you have an in situ probe. So your stack basically comes in this region, and the analyzer is basically inserted into the stack, and you have the light bouncing off a mirror that is placed here. And if you see here, this is a long probe that is inserted into the stack, right? So if you have this long probe, it has several filters on them. And these filters are very, very minute filters, which has a filtration capacity of 20 microns, or even in many cases 2 microns. And they won't allow the dust to come in. Only the gas would diffuse through these filters into the chamber where the measurement is done, and the light is basically passed through the gas to make your measurements. So By doing this again, you can measure many of these concentrations. It is easy to install because it's just putting it in, but it is difficult to remove, in the sense that it will be very heavy because you have so much stainless steel surfaces. So you're talking about a sensor which may be weighing upwards of 100 kgs. So putting it and removing becomes difficult. But the first time installation could be easier. And then it is measuring a true spot measurement. So it is measuring in the place where it is installed, without really altering the gas. So it is original representative measurement. Whereas disadvantages is when you have high dust load, these filters get choked quite often, and you need very high purging. Purging means basically sending high pressure air through these filters and removing all the dust on that. Also, you need very high temperature optical surfaces. If it is 80-90 degrees centigrade, we are fine, but there are applications where temperatures can go as high as 300 degrees centigrade. Then you need these mirrors or optical surfaces to be able to withstand the temperatures of 300 to 500 degrees centigrade. Typically very heavy for installation. Its response time is not as good as a cross duct sensor, because the gas has to diffuse these filters, and that diffusion can be pretty slow. So you have a very slow response time. And there is another type of installation also, where you have what do you call, analyzer kept safely in at the bottom of the stack, and you will have and the stack will have a probe, a small probe, which is basically sucking the gas in, and then sending it through a sample line at a temperature of typically 160 degrees centigrade, so that no chemical reaction occurs. And then the analyzer itself can be placed at a slightly very near to the control room or anything of that sorts, where it would do the analysis. So many people prefer these kind of things, because the maintenance becomes very easy, because everything is on ground. Only a probe is on the top, and probe typically doesn't get choked that often. And it is easy for installation, easy for maintenance. There are no high temperature surfaces. 160 degrees centigrade is still manageable, irrespective of how the system is, how the stack temperature is. And then you have the disadvantages is that it takes physically a large amount of time for the gas to be sucked in, right? So it's typically you would get 5 liters per minute or so as the gas flow rate, 5 or 2 or 3 liters per minute. And that's pretty slow. So it is good for a SEMS kind of SEMS, where it's continuously emission monitoring systems, where it is going to a CPCB for control, CPCB for telling how much emission. It's typically good for that, but not very good for process applications, where you would want faster control, right? And also you need a large real estate. You need to build a shelter, or some of these systems, like what I have shown, could sit outside, but there are other systems which require shelters, which requires air conditioning. So that forms its own line of things, where it can be very capital intensive initially. Okay. So once you have chosen which method you want to use, based on several constraints of finances, or several constraints of the place where it is to be measured and things like that, you would ask yourself, what method of optical detection should I choose? Okay. So in that domain, there is actually an array of technologies that exist. Okay. So let me talk about these three which I've talked about here. Just as a one liner, just tell you that why they are good and why they are not. There is something called gas chromatography, where you would actually mix the gas with a lighter gas like helium, and then pass it through a long glass tubes, where all these gases separate out, and you can measure individual of these gases. Okay. So that requires, it's a very cumbersome cumbersome chemical method, which was used quite often before optical technologies became became available. And even now, for example, standards in US require you to compare your optical methods with your instrument with a gas chromatography instrument. And even now, when you make cylinders, you basically use gas chromatography to check what is the concentration. So that is one method. Then you have electrochemical cells. Nowadays, even they are available even on commercial market in terms of sensing gas leaks and things like that. You can buy an Arduino kit for measuring gas leaks, and they are typically electrochemical cells, which they're basically chemical reactions when interfaced with a gas, which causes an electrical response in terms of change of resistance or change of conductivity or any of that, or generation of voltage. But they're very, very sensitive, but they are not very selective. There can be a plethora of gases which can cause the same change, and the chemical reactions typically decay over time, and you cannot expose the gas continuously to these kind of chemicals. So it's not an ideal candidate for continuous monitoring. Then you have chemiluminescence, also, where you can have chemical reactions emitting light, which can also be measured. Again, that requires different chemicals. What is our kind of importance is optical absorption, right? So in the optical absorption also, there are plenty of things. I'll just name these things so that you can hear the names and maybe go and search later about what they are. But some of these things I will explain. Okay. Then you have basically dispersive techniques and non-dispersive techniques. Then you have Fourier transform infrared spectrometer, FTIR. Then you have tunable laser spectroscopy. So these are basically four major subdivisions. And in dispersive techniques, basically use a spectrometer. I suppose all of you know what a spectrometer is. Spectrometer basically displays the spectrum of the light that falls on it. And we use UV absorption spectroscopy quite a bit using this technique. Non-dispersive infrared spectrometer is something that uses filters instead of a dispersive technique like a spectrometer to do the job. And in that, the two important techniques are gas filter correlation and differential absorption. Okay. And then you have Fourier transform infrared spectrometer, which basically uses a Michelson interferometer to basically move a particular mirror to generate what do you call correlations or interference at different spectrums, which will lead to generation of the spectral profile. And from this spectrum, you can determine. It's actually a very, very high resolution method, and typically labs use them to get good approximation of the actual lines that are existing. Okay, so you have FTIR. But in the field, there are very few instruments which uses this method, primarily because there are moving parts and there's a lot of maintenance involved and things like that. And then you have the latest things like tunable diode laser spectrum. So you have diode lasers, which basically when you pass different currents through them, they can generate different frequencies of light, or what I mean is wavelength of light, which means that because of the change of the refractive index in the medium, that on the laser. Okay, so these tunable diode lasers are extremely you can what do you call pinpoint to a single absorption line. I'll come to that in later slides as to why that is important. And even that, even there, you talk about direct absorption, you talk about wavelength modulation spectroscopy, and even in that, you can use something called a diode laser or intraband cascade laser and quantum cascade laser. So these are terms for you now. You can actually go and do a Google search on each of these names, which I'm not explaining in the later slides, and what they are, and possibly that can help you. Okay. So let's give a brief idea of an UV-based optical spectrum in order to solve our present problem, which is to basically measure SOCs and NOCs and things like that. I showed you the specs that we are talking about, right? So in order to solve that problem, how do we go about? One way of doing that is UV spectrum. So there are available databases which talks about what spectrum exists, what spectrum for what is the spectrum of each of these gases. So this particular graph shows the absorption cross section, which can be, of course, converted into the absorption coefficient, and with respect to wavelength in a UV spectral region. So if you look at this, NO2 has a pretty good absorption spectra between 350 to 400 nanometers. SO2 has a good spectra between 250 to 300, and NO has a good spectra between 200 to 250. Right. So if you look at this as it is, what you need to do is you need a particular source which looks at the spectra at NO2 region, which again looks at the spectra in SO2 region, and which looks at NO region. Okay, so when you see that directly, what comes first thing in your mind is that one is that you need to measure these spectra. You need to measure this and basically sum these spectra. In order, you have to find a correlation between the absorption that has happened to the concentration. That requires a certain amount of calibration. And then also what is important is that at the region where SO2 has spectra, there is also a spectra from NO2. Okay, so we need to compensate the value that is generated from the SO2 spectra in order to remove the interference that is happening over SO2. And another thing that will happen also is that if you look at the NO spectra, it is heavily what do you call there's heavy interference because of NO2 and SO2 on NO, and their interference ppm to ppm basis is quite high compared to the NO2 spectra itself. So it is now not only a spectroscopy problem, it is now a statistical problem, or it is now a linear algebra problem, where you would use different techniques like principal component analysis, or differential absorption, or polynomial fitting, or any of those methods in order to remove these spectra. Okay, and there's a lot more involved which I will not go to for the lack of time, in terms of how you choose the spectrometer, how the spectrometer nonlinearity itself will come into play in order to what do you call when you try to separate the spectra and things like that. So typically, how is the setup? Typically you have a source, a UV source. A UV source is typically either a deuterium lamp or a xenon lamp. Deuterium, as you know, is an isotope of hydrogen, which when excited with a heater and with the electrodes would end up emitting UV spectral region. And then also you have xenon lamps, which also emit in this region. So the light would pass through a heated chamber, where you have the sampled gas coming in, and this heated chamber would give you the spectra. I'm quite okay. Then you also take a reference in silicon using a silicon detector. So you get the spectra. You can always measure the concentration as a ratio of, for example, this is the SO2 spectra. You can always find the ratio of these two spectra, or you can use a polynomial fit method to basically fit a line across this region and then find different concentrations. Okay. You guys have any question right now? I wanted to take questions after this, but I think there is a severe lack of time in one sense. So if you have any question, I can.
Yes, Anish, there are several questions so far. I could try to summarize them, some of which you probably already touched upon. So there was one question about comparison with other types of sensors. Electrochemical, you already mentioned why these optical sensors are better than electrochemical sensors for continuous monitoring. What about vapor pressure detectors? That didn't feature in your comparison. Is that considered at all?
We typically don't use that because see, any method that would require a certain column of gas or has major interferences in terms of identifying whether it is because of what that the pressure has changed, or in terms of maintenance, we typically don't go around those techniques, simply because there is a lot more chemistry involved than the detection principle.
Okay.
Yeah, so typically we don't go through those methods.
Okay.
Yeah.
So it's not so practical for an
Yeah.
industrial
Yeah.
environment.
It's good for labs, but not for industries where they would want a high uptime.
So you talked about IoTs, and I suppose it's a recent phenomena. Maybe previously it was not so prevalent, but is it like a must-have in the industry these days?
Yes. So
Nowadays?
CPCB has basically told.
I know you used that phrase a couple of times. You couldn't really catch that.
Yeah,
CPC?
CPCB is Central Pollution Control Board.
Okay, fine.
It's a central government organization which looks at all the pollution parameters. Okay.
Okay.
So they basically are looking at. There has been several cases of wrong reporting. They basically send out a notice to shut down the plant if the pollution is above, and it's a legal thing. It's a legal thing to shut down the plant when they send notice. So there has been several cases of wrong reporting that has been happening. So they have made it mandatory that all the data from the from the instrument has directly to go to the server, their server. It cannot be routed through any of the computers where manipulation can be done. So that has become now mandatory. It is not good to have. It is a mandatory thing.
Yeah, so I suppose these sensors would be directly plugged into the CPCP, and they will actually have a real-time reading of all these. Maybe in the future, if it's not
They
in the
already
future,
have it.
they already have it.
Yeah. They have a huge server running and looking at every plant emissions, every major plant emissions.
Right.
Yeah.
Okay. And calibration is mandated. Like they would insist that these sensors are like yearly calibrated and so on. Yeah.
Yeah. So it is every 6 months, and they also they want a capability to do a remote calibration. In sense, they will basically press the button for calibration from CPCB, and it has to get remotely calibrated.
Okay, great. So you were talking about this coal burning, power industry environment, and we know that fly ash is a big issue there.
Yes.
So when you're talking about actually having these filters out and all that, so fly ash could potentially clog up the filters, and I wonder whether there is actually selective filtering happening, like some of the gases which are some of the molecules which are smaller actually go through, and some others are not going through. So because of that, you don't have accurate reading of the parts per million.
Yeah. So typically, the gas filter filter porosity is between 2 to 20 microns.
Okay.
With a 20 micron filter, it cannot really stop the gas from entering, because the molecular sizes of these gases are way lower than 20 microns. Right? So what it stops is typically only the dust. And dust can get clogged up, which has to be removed by putting a purge there.
Okay. So that's a forced removal sort of thing. You just blow this off. And then there's one question: what are the top things to consider when deciding between you mentioned several absorption methods, and for a particular measurement, what are the key things that you consider for that?
Yeah, so that's a good question. Actually, that brings right to the slide in one sense of the way, because See, for example, main things to consider are absorption capacity or its strength, and most importantly, interference. If you look at this SO2 at we call something as wave number, which is typically not used in places other than spectroscopy. That's basically 10,000 times 10,000 divided by the wavelength in micrometers. Okay, so if you have 2,500 centimeter inverse, SO2 has pretty clean spectra. Okay, but if you look at NO has major interference from water. Okay, so the sensitivity of an NO measurement in this region is not going to be very high because of the water's interference. So basically, you cannot make a sensor which has 1 ppm sensitivity by looking at the entire spectrum. Okay. However, you can possibly go to the technique that I'm talking about, like IR optical spectra and all, which depends on the lamp. Basically looks at only
broadband excitation.
It's a broadband, so they don't have the capability to measure very high sensitivity, very in the presence of interference. But if you look deep into this cluster of spectrum that exists, what you will find is there will be 1 or 2 lines where the interference is minimum. Okay. So tunable diode laser would do that job. It will go directly to that particular region and get it. But now the problem shifts to a different domain as to you should get a tunable laser of that particular wavelength. Okay. So for a long time, there was no lasers which were operating in the mid-IR region to do that. But now they are available to do that. There you can go PCBs. Yeah.
A related question. So you showed some data on the lower wavelength side, which is, I think, closer to the atomic, transitions.
Yes.
So electronic transitions, and of course, in your present slide, you were the one that you showed just a minute ago. You're going more towards the molecular absorption side.
Right.
So which one is better, or how do you choose between the two?
Yes. So not every molecule has the spectra in the UV region that we can have access to. Okay. So if I want to measure some HCl or carbon monoxide or carbon dioxide, we don't have access to their spectrum in UV region. Okay, so we are forced to come to NIR, IR region. The very nice thing about the UV region in that domain for SOX NOx measurement is that there is practically no interference from moisture. Okay, it's zero. So you can do a very good measurement in that domain. But here, if you come to the absorption levels, if you see the line strengths in the mid-IR region, is almost comparable to the line strengths in the UV region.
Okay.
But there the problem is sources are very difficult to get or very costly. So most of the sensors nowadays, which are in the market, are all in this region. Okay, or they are basically broadband sources. Okay, these are the two things that exist. So broadband sources uses something called gas filter correlation.
Okay.
So it is highly dependent on what technology exists for doing what you want to do. If that if that problem does not exist, then you could go for a quantum cascade laser running at mid-IR region, or you can go for a UV region looking at broadband region.
Okay.
And you would never want to come here, but the technology exists only in this region.
Right. Yeah. So just to clarify, the wave number is inverse of the wavelength. So when you're talking about UV, you're talking about the right side, the higher wave numbers, and when you're talking about the mid-IR, you're talking about the lower wave numbers.
Yeah.
So okay. And then there's a question about tunability of UV source. So that
It's not tunable.
Not tunable,
Not
right?
tunable.
So that is actually a disadvantage if you want to go to UV. And there's another question. I think you might have already talked about it. When two gases have the same spectrum, how do we measure them accurately? But you're saying that although in this graph it might look like it's overlapping, when you look at the individual lines, these fine features within that, there might still be a line which is not overlapping, and you target that line basically.
Yes, yes.
So if other question is, if you're measuring gases at the stack, if limit is exceeded, then I mean, you mentioned that things are going to be shut down, but what do they do internally to get over that situation? How do they treat the gases?
So okay, then what I'll do is I'll just skip one or two slides in order to answer that question. Okay, so that's a better way to do this. See, there is these technologies have not come in yet. Okay, right now, if you shut down, they might have to clean the boiler or reduce their capacity in order to meet the pollution demand. But what is there presently presently abroad, and also which has been mandated now, is to use something called a selective catalytic reactor for reduction of NO. Okay, and also something called FGD, that's called flue gas desulfurization, that is for reducing the sulfur content. Okay, so what a selective catalytic reactor does is that when the NO comes in at very high temperatures, now we're talking about 500 degrees centigrade or 350 to 420 degrees centigrade, you basically inject ammonia into it. Okay, so when you have NO and ammonia, it basically gets converted into nitrogen and water. Okay. And NO2, of course, again forms nitrogen and water. So that can reduce the ammonia content, NO content. But this is like a double-edged sword, because ammonia is also not good for atmosphere. Right? So you need to make sure that you are putting the right amount of ammonia to remove NO. Okay, you end up putting more, you get other problems. Okay, so you typically end up with something like this if you put a lot of ammonia.
Yeah, and there again you need a sensor to say.
Yeah, there again you need a sensor. You have something called ammonium bisulfate forming because of the sulfur present, and as soon as the temperature goes anything below 220 degrees centigrade, it would just clog your whole power plant. That's where you need an ammonia sensor, which can measure sensitivities of 0.1 ppm.
Okay.
Yeah.
Good. Another general question is why wave number is used instead of wavelength.
I think it's, according to me, it's more of tradition.
Yeah.
They were talking
I was looking at this as wave number is basically proportional to frequency, and that is representing energy. So if you're talking about spectroscopy using the energy levels, it's easier to actually see which energy levels are.
I think it all comes from E equal to H nu.
Yeah,
and
that's right.
Always wanted to make the rest of it a constant and nu as simple variable.
Yes. Okay. So that's all for now. So what is going to happen is some people might have a class they could leave, but I think this session is bounded by your time, so people can feel free to leave, and of course it's being recorded, so they can always catch up later. But we'll let you go on.
Okay. Fine. Yeah. So many things that I want to tell in this slide is already covered in the questionnaire. So what we're talking about is if you want to measure any of these gases, you could also have something called a gas filter correlation. Okay, so gas filter correlation is another technique which is far more sensitive than the DOS that we talked about, differential absorption that we talked about in the previous one. So here what is done is that you basically have two filters. Okay, and the nice thing about this is that you have one of these filter is basically of the gas that you want to measure. Okay, so for example, if you want to measure NO or if you want to measure CO2, this particular filter basically has 100% of the gas. Okay, the filter, there will be an optical filter to isolate the wavelength that you want, but it also has a it also has a filled gas in it. Okay, so now when the light passes through this filled gas, irrespective of what gas exists in this region, it is going to have a very, very high absorption, like what is shown in this part. Okay, so your gas absorption basically gets completely nullified, because of the sample that exists is completely nullified because there is a very huge absorption of that particular gas in this region. Okay, and that you call as a reference. Okay, and then what you do is that you basically have a wheel kind of an arrangement where you would take off the filter, and then pass the light directly through the sample. Now you will get the measurement of absorption from the sample itself. Okay, and now the detector, as you know, this is a detector which is not a spectrometer. It is just a photodiode. So what basically will happen is that this whole region gets summed up. Okay, and then falls on a particular amplitude. So you have a particular amplitude that is a very low amplitude corresponding to not having the what do you call corresponding to a complete absorption from a gas filter. And then also you have spectra where you are talking about only absorption from the gas sample. So the ratio of these two is also a very good indication of your gas spectrum, a very good indication of your concentration. Okay, the nice part of this technique is that since you are referencing with respect to a gas, already existing gas, what you can basically do is that your interference gets kind of referenced out in the reference spectra itself, because in both the cases, when there is a filter wheel and when there is no filter wheel, you will still have interference, and the light absorption because of the interferent will also be there in both the cases. So when you take the ratio, they get cancelled out, whereas the gas itself will get a fingerprint, and that ratio will already have these what do you call, the detector will basically get that particular difference or the ratio. By doing that, you can cancel interference quite a bit, but still it is not the perfect absorption. One of our analyzer actually uses this technique, and it's quite a robust technique if you want to measure concentrations of 0 to 500 or 0 to 1000 ppm range. Okay, so these are the if you look at the wave numbers, the different gases basically have different wave numbers that is shown here. So every gas can have multiple wave numbers. The very advantages of this technique is that you can measure multiple gases in a same setup. With the same source, you can actually measure something like 6 to even 10 gases at the same time. Whereas UV, because of the range of the instrument, because of the range of the spectrum that you have access to, you can typically measure 4 at max. Whereas here you can measure CO, CO2, water, like that. So many of them can be simultaneously measured. That is the good thing about this technique. So both of these sensors are actively used in measurement of SOx and NOx, and even CO, ammonia, CO2, and things like that in a power plant. Okay, so let me go to a different application altogether. I explained a little bit of this in my previous questionnaire. So what happens is somebody asks a question like, what if we don't meet the requirement? Okay, then you have to include something called a selective catalytic reactor. So what is a selective catalytic reactor? You basically form combustion using air and coal, and then steam is generated, and the gases that are generated now is not directly left out to the chimney, but rather it is sent to something called a selective catalytic reactor. There are two types, basically non-catalytic reaction and catalytic reaction. Let me just simplify it to a catalytic reaction. There will be a catalyst inside, some by name called vanadium pentoxide, which gets added which in the presence of ammonia, so ammonia is basically injected into the reactor along with your NO and all the gases that exist, and this particular reaction happens. Okay, so you have NO, NO2, ammonia, AO2 forms, and you basically generate nitrogen and water, and that happens only when the temperatures are 360, 400, 500 degrees centigrade. Now you're talking about, so you have effectively removed NO from the system. Okay, so then it goes to something called an electrostatic precipitator, where again you will have you will have charged electric plates, which since most of the dust particles are charged, the electro plates basically capture those dust particles and separate them from the gas, and then those dust particles of course have to be landfilled separately, and then that's how you remove the dust. And then you have something called a desulfurization. So in desulfurization, what happens is you basically put lime into the system, and sulfur reacts with lime and reduces the sulfur content, and then gets into exhaust. Okay, so this is the process. So when you're doing all these things, you have to be careful that the ammonia injected actually creates a big problem. So what it does is something called ammonium bisulfate. Okay, so in ammonium bisulfate, invariably there is SO2 and SO3 in the system. They actually react with ammonia and form ammonium bisulfate. Okay, so ammonium bisulfate, when you when at temperatures about 220, 300 degrees centigrade, they don't form, and even if they form, they are gaseous, so you don't have much of a problem. But as soon as the temperature drops, they become hard solids, and they go and sit into your instrument. They sit in the stages of the power plant everywhere and block everything, and they're so hard that you need a chisel and a hammer to break them open. They are not like you rub it off and they would go off with an air purge or anything like that. Okay, so they are really solid hard blocks. So you need to make a system so that this does not happen. Basically, then we are talking about, so this particular graph is, you can look at this graph later, but I'll give you a gist of what it is. It's a graph of temperature versus the fraction of ammonium sulfate or bisulfate forming for a given amount of ammonia. Okay, so for example, let's take this graph which has circle on it, which is 100 ppm. So if you have 100 ppm of ammonia at 220 degrees centigrade, you will have about 50 ppm of 50 or 0.45 or 45 ppm of ammonium bisulfate forming. Okay, you would ideally want to be at 225 degrees centigrade or above so that nothing forms, but we typically operate at 220 because our ammonia concentrations expected would be less than 50 ppm or 30 ppm. Okay, so you take this line, and we operate at temperatures above 220 degrees centigrade. So now we are talking about a sensor which is not operating at 80 degrees centigrade. You're talking about a sensor which is running at 220 degrees centigrade of temperature, and the entire line has to be kept at that temperature. Otherwise, this white thing will form inside your sensor. Okay, so this is the specs. Most of it is same. Just thing that I want to specify is you're measuring ammonia, and you're at 0 to 20 ppm of concentration, and sensitivity is about 0.1 ppm. Sorry for not putting the unit here, but it's 0. You need as low as 0.1 ppm because people want to keep their ammonia concentrations as low as 2 ppm. Okay, because they don't want that to happen and increase the maintenance. Okay, so this is where I was talking about which line is important. Okay, so if you look at here, I have put things in wavelength scale so that people can readily understand it more clearly. So if you could generate wavelengths of this is basically wavelength versus absorbance. This is the amount of light lost, okay, because of presence of a particular gas. So if you go to like 10.5 microns, you have very high absorption from ammonia. Okay, as you go to 6, as you go to 2, it basically decays down quite fast because these are basically called overtones. Okay, I'll not go into what is overtones and things like that because it will take some time. So you would, as a spectroscopist, you would ideally think that I would want to be here. Then I can do a very, very sensitive measurement of these gases. Okay, but the technology part of it says getting these wavelengths in. See, now so now we are actually talking about individual lines here. That is a difference. Previously, when I was talking about filter correlation and things like that, we're talking about broad spectra, but now you're talking about individual lines, so you need lasers to do this job, and getting a laser at 11 microns is going to be extremely costly, okay, to do the job. So we are actually forced to come down to something called a near IR region, which is booming because of the fiber optic industry. Okay, so you're talking about 1.5 microns. So if I go to 1.5 and 2 microns, this region, the absorption level, if you see, is 10 to the power of minus 4 compared to 0.3 that we're talking about. That's 100,000 times lesser. But that is a laser which you have access to. Okay, so we are kind of forced to work in near IR region. So if you think about direct absorption, you simply follow the Beard-Lambert's law, and the light passes through it, and you have a tunable laser which tunes across the wavelength, and wherever there is an absorption line, you will start seeing a dip in the absorption line. Okay, so in order to make it more sensitive, if you directly do this and measure the peak I0 and I1 and take a ratio, it's going to be hard to measure because of various kind of noise sources that exist. So what you do is you basically modulate it with a particular wavelength, particular frequency of 10 kilohertz or something like that, and then you can see this line. This is basically a repetition. What is happening is the entire wavelength is spanned only in this region, and this is basically this is a repetition. Okay, so what you get is you get an absorption, and you pass it through a lock-in, which is basically multiplying the same frequency with this, and you filter it, and you start getting very good amplitudes, and you can measure with very high sensitivity with this method, because you are offsetting your 1/f noise, and all those things are reduced quite considerably. Okay, so this is one way of doing it. A slightly more advanced technique is something called wavelength modulation spectroscopy. Okay, this is now going one level higher, using a tunable laser. What also happens is that when you modulate this sine wave by using a current modulation, that means you're basically changing the current of the current that is being induced into the tunable laser. What also happens is that tunable laser is tuning based on current, right? So when you modulate the current, not only the power gets modulated, but the wavelength also gets modulated. Okay, so if you look at the spectra in the region, for example, C, okay, there is the absorption is basically flat. Okay, so as you move through the as you modulate the wavelength in this region, you will not see any much power change. Okay, because it's basically flat. This is if people remember FBG based interrogators, they actually work in a very similar principle. But now we are replacing FBG with the actual the gas itself. Okay, the spectra of the gas itself. So as you fluctuate, as you basically move across this wavelength, wave number, you will basically get nothing. There will be no change in amplitude. Whereas if you look at the slope, as you keep changing the slope of modulating, the wavelengths that are in the lower side will get higher absorption, whereas the wavelengths that are wave numbers that are on the right hand side will get lesser absorption. Because of that, you will get very large amplitude of signal, but it will be at the same amplitude as what you have modulated with. For example, if you are modulating this at 10 kilohertz, you will again get 10 kilohertz in this region. But if you look at the region A, what ends up happening is there is a certain amount of mirror symmetry with respect to this point, right? It is a mirror symmetry. So the absorption level on the left-hand side and absorption level on the right-hand side are going to be exactly the same, irrespective of when you move, when you basically change the current with respect to a particular frequency. So what ends up happening is that at a frequency of 10 kilohertz, when you are modulating, you will end up with 20 kilohertz. Okay, so you are basically modulating the wavelength, and now your lock-in is no longer at the modulation frequency like how it was done here. Your basically reference signal is the modulation frequency. Now you basically multiplying with 2 times the modulation frequency. Okay, so when you have 2 times the modulation frequency, you will end up with a waveform which looks something like this. Okay, so if you look at this, the two times the modulation frequency has a peak at the peak, because that is where the 2f gets generated at the maximum, and it has a dip in the linear region, in these regions, because there is no second harmonic being generated, because because the this slope of the absorption line is practically linear. Okay, and then if you look at this region where there is a slopy curve, there is some amount of 2f generated, and you get a spectra something like this. There's a lot more characteristics of this spectra. I'll not go into that for the sake of time, but this peak is now proportional to the absorbance peak. And the very nice thing about this is that you can basically control what is the span of the wave number that you are scanning with every 10 kilohertz that you apply. That means this particular system is is actually sensitive to the shape of the curve. It is not really sensitive to the absorbance per se, but it is actually sensitive to the shape of the curve. Okay, so that means if you have two absorption spectra that are sitting next to each other, which are which are of two different gases, you can basically separate them off very, very nicely. Okay, and there are several other advantages, because you're you're using a lock-in, so you can get a very high sensitivity and things like that. Okay, so this was one of the panel that was installed in one of the power plants. So this is the installation, and this is our ammonia sensor, and this is our NO sensor that is there. So let's look at the actual plot. So the blue curve is basically ammonia, and the red curve is NO. So as soon as the plant injected ammonia into that, you can see that the NO concentration dropped quite drastically. Okay, so this is kind of proof of the chemistry that I was talking about, and you can measure ammonia quite accurately as the concentration as you measure, and you need to find the optimum amount of ammonia to keep this low. Okay, this plant was in its earliest beginning stage. That's why they were putting really large amounts of ammonia. Typically, you would come down to very low amounts of ammonia at the outlet. Okay, conclusion is that spectroscopy is a fundamental to determining concentrations of many emission. Many other methods exist, but they're not so popular. There is no real golden method which can use across all the range and the topology of the systems and things like that. Every application has to be thought through as to what needs. Of course, the state of the art is to use mid-IR quantum cascade lasers. Okay, so I'm done with the slides.
So then there is when you introduce lock-in detection and subsequently wavelength modulation spectroscopy, it was almost as if they are two different things. But wavelength modulation spectroscopy also, you are essentially doing lock-in detection. I suppose you are differentiating them by, one is actually looking at the modulation frequency itself, FM itself, and the wavelength modulation spectroscopy, you are looking at 2FM typically.
Yeah. So so what can the difference between the two actually also depends on how you are modulating the laser source. Okay. Mm-hmm. So if you have, for example, if you have a tunable diode laser and you do a current modulation on that, you will invariably end up doing wavelength modulation spectroscopy irrespective of what you do. Okay, the spectra that you would get even if you lock into 1F would be something like this blue colored curve that is there in this graph. Okay, it would not be an absorption spectra kind of curve that I showed here. Okay, if you want to do ideal lock-in detection amplitude modulation only, then you should use a chopper. Okay, so if you have a rotating chopper in front of the laser, then what you would do is you would do only a modulation of amplitude and not modulation of wavelength at all.
Yeah, yeah.
Then you would get something like this.
Yeah, I think when you talked about this, you were already implying wavelength modulation.
Actually, yeah, no. When I talked about this, I was actually implying a chopper-based system. So this I did not really specifically mention how did I generate this 10 kilohertz modulation on it. That is basically by a chopper. So you would use a chopper and lock in with respect to the chopper's frequency.
Okay.
Whereas here you are doing a current modulation and locking with respect to the current modulation frequency.
Yeah, yeah. Okay. So there is one more basic question is what is the use of lock-in detection? Is it only for reducing the flicker noise?
Yes. So see, there are two important things. One is the flicker noise, the 1/f noise. As you choose a frequency that is coming more and more near to the DC, you will invariably end up with the DC noise, okay, or the flicker noise that goes as 1/f. Okay, so you would ideally want to be at a frequency that is away from the flicker noise. Okay, so that is one aspect. The second aspect is as you go away from the frequency, you can also make very, very tight filters. Okay, so that it can look at only a band of frequencies instead of making a filter at 0 to say 500 hertz is more difficult compared to making a filter at 10 kilohertz plus minus 0.5 hertz, 0.5 kilohertz. Okay, you can get high Q crystals, or you can get even digitally you can make it with lesser number of FIR filters and things like that. Okay. And another very nice thing is that you are multiplying the frequency which has generated the original waveform with itself. So now we are actually talking about coherent detection. Okay, we are not talking about simply measuring it on a detector and putting a filter later to get your job done. But now we are actually talking about balanced coherent detection.
Yeah, so phase sensitive detection.
Yes,
so you're picking only the particular phase that you are interested in.
Yes. Of course, radiation spectroscopy as such has furthermore advantages. That is different.
Yeah, but in general, your information content is closer to DC, I suppose. You're looking at static or quasi-static type of information as far as the gas concentration is concerned.
Yes, so we are basically this is like when you do modulation, when you do modulation and send it through the waveform, especially in wavelength modulation spectroscopy, you are basically upconverting the information that was there in DC to a higher frequency.
Yeah, but it is essentially DC, right? There is because in all of these cases that you were talking about, it's extracted gas samples. But in case you were to do this online, even as the gases are moving around, what sort of measurement speeds would they require there?
Extract typically you do not have changes in the gas concentrations more than a second or 2 seconds kind of things, kind of frequency, right? So people don't want that fast because they cannot operate their valves to correct it that fast.
Even if they measure, they're not going to be able
even
to
if
do
I give them a millisecond resolution, what will they do with it?
Yeah.
Okay. So typically, state of the art would be measuring at a millisecond rate. State of the art would be measuring at a second rate, okay, in emission business. But of course, there are other technologies like explosion measurement in shock tubes. Okay, there we are looking at high concentrations, but we are now talking about millisecond acquisitions, because the entire explosion will be over by the time you have measured if it is a second resolution. Right.
Yeah,
So there we are talking definitely about high speed acquisition. But in emission industry, it's typically a second is very fast.
Okay. So then, yeah, it's essentially taking the DC and you are going to a higher frequency, and then
Yes.
Essentially doing the detection and down converting, beating with the reference signal, so you can down convert it.
Yeah.
Okay. Yeah. So I suppose one last question maybe. UV sources are not tunable. That's what you mentioned previously. The whatever is available. So how you perform UV spectroscopy in that case? Yeah.
Spectrometer. We have to use a spectrometer.
Yeah.
If we can't tune the source, we tune the detector.
Yeah. So you cannot do all these tunable diode laser spectroscopy
you cannot.
type of things there. Yeah.
No,
okay. Okay, well, that's a wealth of information. Okay. Maybe on last question. Okay, resolution of a sensor and minimum detectable limit synonymous.
They're related depending on your noise. Okay, so I have not mentioned here about the noise sources. You have different noises like 1/f noise, you have thermal noise, you have in wavelength modulation spectroscopy, you have something called echelon noise and things like that. They are synonymous as long as you are talking about thermal noise or flicker noise. Okay, so if your system has come down to your thermal noise limit, then more the averaging you do or more time you take to make a measurement, better sensitive your system is.
Lower detectable limit.
Yeah, lower detection limit, lower sensitivity you will get.
So that's okay. That's also a related question. So when we say sensitivity, some people look at it as the slope of your response.
Okay.
Right. So there is confusion because we talked about sensitivity in communication scenario. It's the minimum detectable power.
Right.
Or in this case, minimum detectable concentration. Right. But there is also this other thing. So in the class, we have talked about sensitivity as the slope of the response, and minimum detectable limit is whatever it is. Yeah, it is actually the lowest.
I think it stems from the fact that how they define a sensor versus how they define an instrument. To some extent. If you are talking about simply a sensor which is acting like a transducer, which is converting from one physical quantity to the second like current or voltage, then slope is a good estimate because you are not really talking about noise or anything of that sorts in that context. Okay. But whereas when you talk about a system, slope is not what is important to me, simply because I am finally going to get a number out of it.
Yeah.
The final user is going to get 100 ppm. He doesn't care whether what is the slope of change with respect to one quantity to the other.
Yes.
So there, when we see sensitivity, the question is minimum resolution or the lowest detection limit, which sometimes may not be the same. Whether you can measure 100.1 or 101 is one level. So there is again splitting of resolution versus LDL. Okay.
Yeah. Okay.
Yeah. So that's why there's an organization called TUV, which is in Germany. They define our standards as to what your instrument should really do and what tests that they will do to determine your system capability. And they define is that they put if you're measuring 100 ppm, if your maximum detection capability is 100 ppm, they put around 90 ppm of gas inside and look at the fluctuation of the gas amplitude. The measurement.
Yeah.
And that has to be less than 2% of your full scale reading. Okay. And they also put interferent. If you have NO, they also put
Cross
10% of
sensitivity.
water in it. And see how much change has happened with respect to this NO.
Okay.
Measuring 90 and they put 10% water, how much increase has happened? Okay. Now that also should be less than 2%.
Okay.
So the cumulative average should be less than 2%, and that's what they define as your lowest detection limit.
Okay. Okay. Great. Well, thank you. Thank you so much for patiently answering all our questions and also giving us so much information to munch on. I think we will have a feasty lecture session tomorrow where I will have to answer some questions as well. So
Okay.
thank you for providing all that information.
Thank you very much.
Okay. Thanks, Anish. Catch up later.